All right, can you hear me? Hello? So welcome to 120. If this is not the course you signed up for, now is the time to leave, because we'll start really fast and cover a lot of things today. So, first some logistics, and I'll try to keep this short. So you're in 120, you know that, and my name is Murat. First name is good enough. And office hours are tentatively set to Tuesdays, 2 to 3 p.m. 2 p.m. is when the class ends. So the assumption is that if you want to talk to me, ask questions about the upcoming homework, we would kind of walk back to my office together. And along the way, probably the crowd following me will start thinning because people will get their answers or get frustrated with me and just drop. But then the room is actually my office, so we can't stand here forever, right? So other class will come in. So we have a great team of GSIs, undergraduate TAs, and all that. So I'll introduce them one by one. So Dominic here is our head TA. And he's gonna be managing everything about the course, logistics as well as technical things. So sorry for springing this on you, but could you say a few words about yourself, what you do, and maybe something interesting outside of weeks, Sure.
Yeah, hi everyone, I'm Dominic. I'm a fourth year East major. This is my third time TA 20. I'll also be teaching a discussion session tomorrow. See a lot of you there. Outside of class, I like to go soccer.
Midfield?
Defense.
That's what I used to do when I could run. Actually, let's go in order. Where's Ilya? Oh, Ilya said he's going to come late. Well, you'll know when he comes in. He's a character. So, Alex is here.
Hi everyone.
He's like what? Really? Oh, I didn't know that. Awesome. Okay, cool. I'm learning too. So next is Jonathan. Hi. I was expecting something a little juicier than that. And finally, Mindy. I feel like I'm introducing a jazz band on the drums, usually, and you have to play your thing a little bit. Yeah, she's obsessed with bats. Any questions you have about bats? So class hours and rooms, you know that already. Recitations, this is important. It starts tomorrow. Okay? Presumably you're registered to one of these 3 sessions. Are they allowed to move from one to the other, or?
Yeah, as constraints allow, I'm guessing that the first one is going to be pretty close to priority.
Right. Right. I mean, we would strongly encourage you to go to the last one because that will be the least probably popular. But you'll get more airtime to ask your questions and stuff. So those will be in 521 Corey, one after the other. Website. So there is a department website for courses, course material and all that. I usually wait until the end of the semester to dump everything in there because it's too much work to send them one by one, make sure they are there. So we use B courses. So that's what we're looking at now. And I request that even though we're going through this, you look at this page yourself again, go through everything, make sure you understand everything. So for discussions and polls, as usual, we'll be using Piazza. So did everybody get it that tomorrow we have the first discussion sessions? Okay. All right. Textbook. Really, there is none, but there is a book that is, widely used and accepted to be a standard textbook in this area. It is ridiculously expensive. For that reason and other reasons, I don't require this book. But if you would like to, own one, it's not a bad book to, display on your shelves and impress your friends. It is generally a good book. I studied from that long time ago. That also says that it's a sort of dated book, but so yeah, it's a good book. So but you can also check it out from the library. It's on reserve for a 2-hour loan. Okay, so you can take it out of there and take a look. But what I'm going to do is I will, after the lecture, within hopefully a short amount of time, on B courses I'll be posting a clean set of notes. Okay? I usually do that for courses I've taught more than once. So they should be enough, if you're coming to lecture and looking at the class notes, probably that's enough. But if you need more information, more details, you can go to the book. Okay? So about my notes, sometimes I'm asked, why not put a little more detail. I like to make it really condensed and, very short. But the most, the essence of the course, I want to put them in the notes, not things that you can derive by adding two things together, right? So that's just a matter of style and taste, so don't question me on that. So I'm not going to give you like 15 pages of notes every time. It will be more like 5 or fewer. All right, so we talked about the textbook. Again, it's at the library. It's probably the engineering library on reserve for 2 hours. Grading. So before grading, first there'll be homework weekly. Either homework in the paper and pencil sense, or a Jupyter notebook where you actually fill in cells and do some computations. In fact, one will be assigned already today. All right, so we're not losing any time. But the first one is sort of introductory. It sort of introduces you to Python and lets you do a few simple things. So it's by no means an ordeal to do it, but you should definitely work on it over the long weekend if you can. So Dominic will post it today, correct? So you already have a homework or a lab, okay? So lab doesn't mean lab where you look things up. It's a Python lab. Any questions about that? No? Okay, so that will be homework and labs combined will be about 15% of your grade. They'll be weekly most of the time, except when we have a midterm coming up. So that week we may skip the homework or lab. And there's going to be 2 midterms and 1 final. The final date is not up to me. It's determined by campus, and they put it on December 20th. So if you are planning to take a vacation, forget it. You will have to be here. But after that, you can go. So the midterms, I set them. So the second midterm is November 14th. The first midterm is on October 3rd. Tentatively, this might change. Okay, probably not, but the final is set in stone. That can't change. The midterms might, but don't ask me to change it just because it's more convenient for you. There are 150 of you here. Okay, what else? So this is a rough outline. So we'll start talking about basic signals and systems today, and we'll quickly get into linear time invariant systems. This is a special class of systems that have remarkable properties that make them easy to analyze and build, if you can find linear elements. So, and we'll talk about them, and we'll talk about Fourier transforms. So how many of you here took 16A and B? Oh, wow. Okay. So you saw something like a Fourier transform there. It's called the DFT, and we introduced it as a change of basis in that course, which is not the traditional way of introducing transforms, but it's sort of a linear algebra way of introducing transforms. So in this course, we'll follow the more traditional route of getting into transforms, but we'll go back and link it to how we did it in 16. Okay, so hopefully the loop will close, maybe, and everything will sink in finally. I know not every one of you loved DFT in 16. All right, so we'll talk about sampling, how we sample continuous time signals, and how fast of sampling is fast enough so you don't lose any useful information in the signal. We'll talk about several other transforms that go beyond Fourier transforms. These are called Laplace for continuous time signals and Z for discrete time signals. And then we'll try to put these transforms to use. In particular, we'll talk about how we design control systems using these transform ideas. And there will be some application examples throughout the course. And perhaps at the end, we'll have something more of a deeper dive into one topic to be determined. Okay? So, we talked about the GSIs. Take a look at the B courses yourself. Exam times, please take a note. Put them in your calendar. If you're a DSP student, and that's not digital signal processing, it is, that means you need more time on exams. Please send me an email. If you haven't done any paperwork, and if the DSP office doesn't know you're entitled to more time, this is the time to do it now. Okay, before the exam, there's a very tight window for us to arrange things. Okay, so do that if you haven't already done that. If you have, still send me an email so I can compare what you're saying to what the DSP office is saying about you, and any conflict in those statements are resolved now, and we don't have to bicker later. Okay, good. Lab is due. Lab will be assigned today, and it will be due next Thursday. Usually it will be on a Thursday cycle, okay, for the assignments. And we have you covered, if you have questions about the assignments, which I'm sure you will, we have you covered with our office hours. So mine are on Tuesdays, and all of your GSIs and TAs, that's why it looks like it. We didn't put your... Okay, got it. Okay, so I think, Monday, Tuesday, Wednesday, you're covered, right? So nothing, yeah. So you can go talk to one of us. If you have a favorite, go to them. And what else? I think that's all I want to say. So this is going to be a screencast. So supposedly it's happening now. Okay, so I'm recorded and you can see what's here. This is no substitute for coming to class. Please do come to class, right? We'll try to have fun in class, and it's more interactive. It's very boring to watch. I watch these things sometimes, not myself, but others teaching other stuff. And, it's not the same when the person is there in the flesh and, talking about the material. Any questions? Shall we start? Okay. I was on leave last year, so I haven't taught in a long time, so let's hope I didn't forget how to. So I like to use these good notes, and right here, sometimes there are glitches, but hopefully nothing will happen. So today we'll talk about signals and systems. What are they? You probably have a good idea already, but we'll be a little more accurate about the definitions of these things. And then we'll start zooming in on a special class of systems that we call linear time invariant systems. I told you this is a very special class, and you can reason very efficiently about the behavior of such systems. But first, what is a signal? Basically, what we mean by a signal is a function of one or more variables. As simple as that. So when you're streaming music, that is a function, the signal you're getting is a function of one variable, which is time, right? There's only one variable. When you're looking at a JPEG file or an image, that's a function of two variables because it's a two-dimensional object, right? X and Y. When you're watching a video, it's a signal of three variables. There's time as well as the two dimensions. So you can add many examples yourself, but in this course, I would say 90% of the time, we will talk about a function of one variable. Okay? If this were an image processing course, we would be mostly talking about a function of two variables because that would be the image, right? But more traditionally, signals and systems is done with sort of time in mind, although the ideas are broad enough that you can expand them to however many variables you want. And in fact, we will occasionally talk about examples from image processing, so we will have variables other than time. Okay? So again, this one variable doesn't need to be time. It can be anything else. It could be distance if you're looking at functions of a spatial variable, right? But usually, again, for historical reasons, we'll usually call it time. And in fact, we'll denote it as t because the time. Okay, this is not happening. Uh-oh, we have a battery problem. There's still one bar. Okay, when we take a break, I'm going to replace the battery. So, now, signals can be either in continuous time or discrete time. So, continuous time means you have time axis and the signal is something like that, right? X of t. So, it's a continuous function of time. And then we'll talk about discrete time signals, where the time instants are discrete. They are integers or integer multiples of a sample time. In that case, we will usually use the notation n because n is usually, an integer, although it doesn't have to be, of course. So, and then we'll use these plots where the value of the signal at time 0 will be denoted with a circle and a stem, right? So this is x of 0. And then at time 1, you may have a different value, x of 1, time 2, x of 2, etc., right? So, to distinguish, just so you know whether I'm talking about a continuous time signal or a discrete time signal, for continuous time, we will use x of t with these brackets that are round. And for discrete time, we'll use square brackets, just to remind you that this is discrete, okay? No other reason. It could just as well be that, right? And also, as a second reminder, we'll typically use the letter n for time, so that it's an integer. So 0, 1, 2, etc. Okay? So, what is an example of a continuous time system? Or signal, rather. Like when I'm talking to you, pressure waves are reaching you, right? So that's a signal, and it's presumably continuous time, right? When you're streaming music, though, you're only receiving samples of a continuous time signal. It was recorded. When it was being recorded, only samples in time, but many, many samples per second, of course, were kept. So that becomes a discrete time signal. So a lot of discrete time signals come from the discretization or the sampling of continuous time signals. Like digital images is another example, right? Like JPEG, it's pixel by pixel, so it's discrete, not time, discrete in space. But there are, of course, signals that are inherently discrete. They are not just samples of a continuous signal. Can you think of examples? Anyone? Something that's really discrete. Not discrete because you look at it only so many seconds. Yes. Yeah, I'm not sure if it happens on. Yeah, okay. Yes. I think it's good enough. Yeah. I mean, they don't happen at regular intervals, but Yeah, it is still discrete. I mean, events are discrete. Okay, fine. Yes? That's similar to that, yeah, okay. How about something that happens at regular intervals? Yeah. How do you record them? Why is that inherently discrete? Yeah, but again, initially the signal was, I mean, doesn't matter, but the signal initially was a continuous time one, right? That got sampled. So I was asking for an example where something is, by its very nature, happening at certain intervals of time. Okay. That's again a little, I mean, it doesn't really matter. It's a good example. But again, it's something, rotation is something continuous, and only because I'm sitting here and seeing it only so many seconds, it is sort of more like sampling. Come on, someone. Yes, perfect. Homework assignments. Traffic lights, every 15 seconds is a new cycle. It can stay green, but there's a certain time interval. Anything else? Okay, we can talk about this forever, but okay. Huh? Mm-hmm. Yes. Why are they discrete? Oh, I see, like that. Okay. All right, so fine. You can think about those forever, but yeah. Okay, so you get the idea. Continuous and discrete. All right, so we will need to transform this variable sometimes, and at the end of this lecture you already see the need for that, right? So for example, let's say, so basically we're talking about transformations of the variable, in this case time, right? So suppose I give you a signal like this. I'll try to impress you how straight I can draw. Are you impressed? It's this button that does it. Anyway, so let's say our signal looks like this. I'm going to try and make it not even, so it looks different on both sides. Yeah, that's good. So, okay, so this is t. This is my x of t. Okay? So, now if I ask you what x of t minus capital T looks like, choose a number, your favorite number for capital T. What would that look like compared to the initial signal? It's shifted, right? So you can call this a shift or a drag. So you're basically dragging. So if capital T is a positive number, in what direction do I drag it? You go right. Okay, so let me try. So it would be something like this. 2, 4. And I tried to put the peak at 0 initially so that we know how much it moved. So at t, that peak would happen. Okay? So the operation we did here, let's give it a name and be consistent with it. So we dragged it, right? Alright, so what if I ask you about x of negative t? What did I do then? T, what does x of negative t look like? You flipped it, right? So the left side is now appearing on the right, and the right side is now appearing on the left. Okay, so the operation we did here is flip. Okay, now comes the most frequently used transformation in this course, and you'll see in 1 hour no more why. Okay, so what's happening? So what does, so these are all t's. So what does x of t minus capital T, wait, what am I saying? X of capital T minus T look like as a function of little t? Drag and flip, or flip and drag? It's a good question, right? Which one? Let's take it both. How many of you think it's flip and drag? How many of you think it's drag and flip? Okay, the majority abstains, so I guess we have to work through this. Okay, so let's work this out then, if it's not immediately obvious. So, well, I can think of this as two things, right? Well, first let me give you the answer, and then we work through why this is so, okay? This is actually flip and drag, then drag, and the two things do not commute, they are not the same thing. So what does flip and drag do? When you flip it, you define sort of a new signal, right? Y of t is x of negative t. So y is this signal that you see on the on the left, lower left, right? That's what, let's call that y of t, right? And then I drag it, so I define a new signal that is z of t, which is y that is shifted in time, right? But if I combine the two definitions, right? So y was defined as x of negative t, right? So what that means is, whenever I see a t in here, I should replace it with negative t, right? Wait, am I doing this right? No, why did I flip first? You guys are all sleeping. This is... Did I do this right? No. No, flip and drag, right? TAs help me. Flip and drag. Oh, yeah, of course. I'm sorry. Okay. Yeah. Okay, so I need to, what I did wrong here is this. So z is fine. It's y of t minus t, right? But y of t is x of negative t, right? Why am I blanking out on this? What's that? Yeah, that's right. So I'm flipping the sign of whatever is inside. Thank you, Alex. I need the TAs here to save me from occasional trouble. Okay, so this is indeed flip and drag. So what really happens is you are going to drag what we have here so that it occurs at t. So it's going to look like something like this. Okay? X of t, this one, right? X of t minus t. Okay. All right. So what would happen if I dragged and flipped? Drag and flip. Pictorially, it's easy to see what happens, right? You drag and then you flip. So it's going to look different now. So it's going to look like... So what's dragged here is going to flip, so it's going to look like this, right? So something like this, right? Negative t. So how would you express drag and flip as x of something? What would go in there? We're not putting anything outside because that changes the sign of x. We're not messing with the sign. Only things inside should change. I mean, you can presumably do what we did here. Let's introduce some new variables. So by dragging, I introduce a new variable. Let's call it new signal. Let's call it v of t, which is x of t minus t, right? And then by flipping, I define a new one. So let's use different v and let's say w, right? W of t, which is v of negative t, right? So this is the first operation, drag, second operation, flip. So, but what this indicates is that look at v of t, and when you see a t, what did I do again? Oh, okay. I didn't do anything. Okay, good. Yeah, okay, I'll try. Yeah, I don't know what to do. So, okay, I'll go to the next page. So, x of t, we started with x of t. We dragged it, so we got a new signal, v of t, which is x of t minus capital T, right? And now you flipped it, so you get w of t, which is v of negative t. But v is equal to this. So all this says is that look at v of t. When you see the variable t, flip the sign of that, right? So that's going to look like x of negative t, negative capital T. Okay? So the takeaway here is drag and flip is not the same as flip and drag. Okay? And you should be able to associate each of these with the form of the signal we're talking about. So x of capital T minus t is the flip and drag. So, and this turns out to be the most important for us, because we'll do that a lot in doing something called convolution, which we will see shortly. Yes. So the explanation is, I had a pointer, I don't know where it went. Ah, here. So the explanation is here. So flip means, so you take x of t and you flip it. That means you generated a new signal that is y of t, that is x of negative t. Agree with this? And then the next thing you do is you drag the resulting signal. So z is y, drag. No, because y is x with whatever is inside changing sign. So the whole thing inside has to change sign. So that's why it turned it. Okay? So, homework that is not going to be graded or turned in. Take a few signals and play around with them. You know, do these things. Flip and drag are easy, but you know, do the drag and flip and convince yourself that that's really what you're getting. Okay? Because that's going to be important when we learn about convolution. Okay? Can I move on? All right. So let's talk about a few famous signals. They are not called that, I'm just calling them that. So I'm going to stick to discrete time for now. Okay. So one of the most famous signals is the so-called unit impulse. And it is an impulse, which means that it happens only once and then dies off, right? So at time 0, it takes a value that's non-zero, and then afterwards, it's all zeros. And then before, it's also 0. And because we call it unit, the value is 1 at time equal to 0. Okay? So this guy has a letter denoting it, delta of n. So in this course, delta means impulse. Okay? Delta is impulse. If you really want to define it more mathematically, it's just very simple. 1 if n is equal to 0, 0 if n is not equal to 0. Okay? So that's one of our famous signals. There are many others, of course, but let's talk about the unit step. Again, unit means the value is 1 when it's not 0. And step means at time equal to 0, I jump from negative values to 1. And this time, I actually stay there. Three, 4, etc. Okay? And soon, in the coming lectures, we'll talk about exponentials and complex exponentials, things like that. Those are other famous signals, but for now, we are good with these two. They have continuous time variance as well. The unit step should be obvious. It's a step, right? It's a discontinuous function of time. It goes like this. The unit impulse is a little funnier in continuous time, so I'll probably save this to another lecture for maybe the next one. We'll start by talking about that. So let's stick with discrete time. In discrete time. All right. What else? Can you? Oh, the unit step you will denote it as U of n. U for unit step, and then that really means 1 when n is 0 or more, and 0 when n is negative. Okay, so we have delta, we have U. Can you tell me the way to write delta of n? Can you see this? Yes. In terms of unit step, U of n. Now that you know some transformations like flipping, blah, blah, shifting, dragging. Anyone? Can I write it as U of something minus or plus U of something else? Right, so U of n is this signal, U of n minus 1 is the same signal shifted, right? So U of n minus 1 is going to be this. It will be 0 here and 1 after. So this is U of n minus 1 dragged by 1, right? And if I subtract the second from the first, all of these guys will cancel except for this one. So what remains is the delta, right? Yes? Say that again? Yeah, discrete time signals. Signals, you know, we call them basic. I mean, signals are basically functions. In this course, we call them signals. Did that answer the question, or maybe I didn't hear it? Okay. Well, it's a function of a discrete variable. So that's how we represent it. So function doesn't have to be, you know, so the function can be from Rn to something, or R to something, right? R to R, or it can be from integers to R in this case. So you can choose however you want to represent it, but these stem, what we call stem figures, are very standard for representing a discrete time signal. Okay? Any other questions? All right. So now that we're at it, can you tell me a way to write U of n, the step, in terms of delta? Great. Delta of what? N minus 3. You're right. So you have delta of n here. Delta of n minus 1 would be the same thing, except it's shifted by 1, right? So this guy would move here. Delta of n minus 2 would move there. So if you add all of them up, you generate a unit step. There is Ilya. So Ilya, you're supposed to say something about, you know, who you are, what you do in this department, and something else that's about what you do when you're not in this department.
So my name is William Jurnow. I'm with When I'm in this department, I'm focusing on business processing and MRI science. When I'm not in this department, I'm focusing on getting the highest score in technical problem, which is using human getting variance.
Oh, okay. All right. So we're done with signals. Now let's talk about systems. You know, system is a very broad concept. You know, in every field it means something else. But usually what it indicates is that you have a collection of things, things working together. So for the purposes of this course, it's a process by which input signals, we'll call them inputs, signals are transformed to output signals. Okay? So that's a very much, signal processing viewpoint of a system. So what you have is you have a signal coming in X, and then there's this box in the middle, which we call the system. So X is your input, and the system does something to it and spits out an output which we will denote as Y. Okay, so that's what a system means in this course. Okay, you can argue whether this is a good, broad enough definition of a system, but for the purposes of this course, this is what we call a system. Okay. Now, a system can be continuous time, in which case you have an x of t signal coming in and y of t signal coming out. Actually, I'm not going to write these. I'll just write x, y. So understand that x and y are signals. Okay. So if it's a continuous time system, then the inputs are continuous time signals, and what comes out is another continuous time signal. For a discrete time system, the input is discrete time, and what comes out is another discrete time signal. Okay, so they also can be continuous time and discrete time. Some examples. First one is, you said almost all of you took 16, so we bored you to death with these circuits. So you have, let's say, a voltage source, and let's say the voltage we apply is x of t. Okay? And then there's the resistor R, and then the capacitor C. Okay, and let's say I'm reading out the voltage on the capacitor, and I call it y of t because that's my output. Right? So that would be an example of a system, right? So what would define this system, right? So do you remember some equations from 16b? I think the dynamic elements, well, actually both, right? So what is the current that flows here? Sorry to do this to you if you thought you were done with these circuits. So what is I? Yeah, anyone? Yes? Yeah, so x minus y divided by r, right? Kirchhoff. Okay. Oh, not Kirchhoff yet. There's no Kirchhoff here. There's nothing. It's simple. You actually, I think you gave the answer after multiple steps. Yes, there's an exponential, but we're not going to go into that now. So what's the relation between the capacitor voltage Y and the capacitor current I? Okay. All these lectures, all these blood and tears. Huh? Okay, so that's C times dy dt, right? Alright, so what that means is that C times dy dt, let's multiply both things sides by r so that division goes away. RC dy dt, move y to the right, plus y equals x. So this is a differential equation, first order, and somebody already knew it as an exponential solution, but we don't care about that now. And you would have to fix the initial condition somewhere, and let's fix it at 0. So initially the capacitor was not charged. So then this is a description of how this system behaves, right? All right, just to check your intuition. This is not an exam or anything. If x of t is like a super wiggly signal, what would you get at y of t? Decay, I'm not sure. I mean, because that wasn't at centered at 0. But the point, I mean, I should tell you what's up. I made this silly picture. That means something moving really, really fast, right? And will the capacitor respond as fast? So you'll probably get some slower version of this signal, right? So that's an example of the system view in this course. You have inputs, it gets processed, and you have an output, right? This is like me trying to get my son to school in the morning. You come on, get dressed, you know. I have to go. All right, makes sense. So this is a continuous time system. Let's also talk about a discrete time example. So I'm going to tell you about what's called a moving average filter. So here you're doing a basic discrete time computation. To calculate y of n at time n, you look at the input, not just at the current time, but the previous value of the input, okay? The present value of the input, and the next value of the input. So you add them up, and you divide them by 3. Why? Because I added 3 numbers, so I'm taking the average. Okay, that's what makes it a moving average, right? As the time advances, I'm doing this average over the next 3 signal values. All right? So that's an example of a discrete time system, right? And so, and what does that do? Again, if I have a wiggly discrete time signal, what would this averaging do to it? Like something that jumps between different values. I guess a longer one would be a little more informative, but let's just stick to 3, a window of 3, right? So if the inputs are +1, -1, you don't see what that's about here. Okay, I'll try to squeeze it. So something that changes every time, changes sign from 1 to -1, okay? What would you get when you start averaging those? At any given time, you're averaging 3 consecutive things, right? You either get 1/3, or you get -1/3. So you have eliminated those wiggles to some degree, right? In fact, if I had an even number of these things that I'm averaging, I would have completely eliminated the wiggles at the output, right? So 1/3. So we should have done 1/4 so they completely go away. That doesn't matter, okay? So these are both systems. One is in continuous time, the other is in discrete time. Turns out they are both what we would call low-pass filters, because these are filters that eliminate high frequencies. High frequency means wiggles, like quickly changing things, right? So those get eliminated. Okay, so those are systems that filter out high-frequency components in the incoming signal. All right, I've been told the human cognitive skills or process decays after an hour. In fact, after 18 minutes, they say. We'll make it an hour. You know, you've probably seen these TED Talks. They are all 18 minutes. Supposedly 18 minutes is the limit when you start getting distracted. Let's take a short break, maybe 5 minutes, and then we'll continue.
possible to do, or if I should like switch out of 120 sessions or another?
No, don't switch. I mean, if you can manage, well,
Yeah.
if other obstacles arise along the way and you think overlap is a problem, then maybe. But exam, we can accommodate you. Because the finals I looked also, they are different
Yeah,
days.
they're different.
Second midterm seems to be different.
Yeah.
So we'll just put you with the DSP students in a different room.
Okay.
So you can have half an hour extra. You can start a little late. Or we can, but you have to remind me, absolutely.
Yeah.
Don't say, I told you 2 months
Yeah.
ago and you forgot, okay?
16B is technically a prereq. Is that because are we going to need to have a basic understanding of circuits this class, or is it mostly just none of that?
Did you take it or not?
No.
You're
But I
fine.
said transform.
I mean, I think prerequisite means it would be great if you had it. I don't even, I mean, I'll have some examples. This is not a circuits class. There may be an example here and there.
But not like critical like that.
No.
Okay.
Like anything of this sort, do you understand what's happening? Okay.
I don't understand.
Okay, I mean, so the thing is,
Shouldn't matter. Okay.
there are two basic rules, right? So if you have a capacitor,
Yeah.
it goes with a number that's called the capacitance.
Okay.
So the current that flows through the capacitor and the voltage are related by C times dV dt is equal to I of t. Okay?
Okay.
If you have an inductor, and that's the symbol for it, because it's like a solenoid, then the inductance is called L, usually the symbol for it, right? And then the relation, B, is L, this time is reversed. L dV dt, no, di dt, sorry. dt is V of t. Okay.
Okay. This is
Voltage.
voltage. Okay.
Okay?
Okay.
Now, then you have a resistor. Again, voltage. Current. Voltage is I times the resistance. No memory here. These guys have integrations, right? And when you put them together, like in this loop, so there's a voltage source, V. There is the resistor voltage, so the current is flowing this way, let's say. You just, by convention, you say, current is this way, it can be negative, right? That means it's flowing the other direction.
Yeah.
And then you have the capacitor, C, and the DC is the capacitor voltage. So you need to know, the positive and negative ends, right? So the voltage is along the loop has to add to zero, right? So you have V here, that needs to be matched by VR plus VC.
Okay. So
That's one of the Kirchhoff's laws.
initial condition.
No initial
That's not it,
condition. Just the sums have to, the sum around the loop has to be zero. But because of the signs, if I split the sign, this will be negative V. So this is the same as saying that, okay?
Yeah.
This is the first Kirchhoff law. The second one is if you have a current and if it's branched into two things, I1 by 2, I1 plus I2 is I.
Okay.
There's nothing else. This is it.
So I just need to have an understanding of the basic rules and then
But take a picture of this and look at the example, how you put them together to get a differential equation.
Okay.
There's nothing more than that you need in this course.
How can you tell from looking at the low pass, the moving average, that it's low pass?
I don't. I mean, I sort of intuitively saying that, if there are high quick changes, because I'm averaging out, those quick changes will be averaged out.
Quick changes from 1 to negative 1?
Right,
Why
right.
is 1 to negative 1?
Oh, any quick change. Like, let's say you're taking an exam every day, okay? But you're very erratic. One day you max out, you get 100, the next day you get 50, and then the next day you get 100 again, and then you get 50 again, right? At the end of the day, you look at your average, so it's somewhere in the middle, right? 75. So if I take a window of days and average your scores around these days, that erratic changes will go away, right? Will be averaged out. You're averaging, it's a window of time you're looking at, you're averaging the values. So it has this filtering effect. We'll be much more precise about what we mean by filter, what we mean by low-pass filter. Don't worry. But this is just for some intuition. Okay? Sure. All right. Okay, are we ready? Yes, thumbs up. Okay, so we'll talk about some system properties. Okay? Every system is different, just like every student is different. So we need to find ways to, classify them. Is the great student, is the lazy student, that kind of thing, right? So a memoryless system, what does that mean? Well, it means a system that has no memory. It's evident what it means. So the output at any given time depends on the input only at that time. Not the past, not the future. Literally memoryless, you know nothing about the past. You don't remember anything. Okay? So, here's an example. Doesn't matter. I mean, same idea basically, continuous or discrete time. But if I tell you that y of t is, let's say, x of t squared, does that involve any memory? I don't need to know anything about the past or the future, right? So it is a memoryless system. So if we go back to the examples though, let's look at the RC circuit first. Was that a memoryless system? It's not because right. Capacitors have memory, right? I mean, they remember things. They, like elephants, they will not forget what came before. So, the moment, in fact, you have a differential equation, right? That means something is being integrated and all that, right? So, you can't just erase the past. It will affect the future, okay? So, therefore, this is not a memoryless system. It's a system with memory. I don't think you say memory full or something. It's a system that has memory. What about the moving average filter? Well, y of n depends on x of n minus 1. I mean, it's not just x of n, right? So that obviously has memory. For discrete time systems, a memoryless system is basically one that you can build without memory registers. You don't need to store anything and then recall it. Okay? So as simple as that. So I don't think we need to talk too much about memoryless systems. But a physical example, I was giving a crash course in 16 here. So basic memory elements, basic circuit elements. So these guys obviously have memory because they're integrating something, right? They will remember the past values. The only memory of this guy here is a resistor because the voltage is going to depend only on the current at the same time. The physical question, I don't know the answer really. Maybe Alex does. So is there anything that really has, is there a resistor that really has no memory, nothing? No capacitance or inductance because of the wiring or electrons jumping up and down? So that would be an idealization, I guess, right? So, I mean, I think at some level, at some time scale, there is probably still some memory. But as a first, as a simplification or an idealization, this relationship, all of these are idealized relationships, right? There is no circuit component that really obeys this, perfectly. But this representation at least is a memory this time. Okay, so that's memory. Causality. Causality. Or actually, let me be consistent. I said memoryless, so let me say causal system. So what is a causal system? Well, okay. Causal if output depends on input at present or past times, not the future. Okay, so the current output at this point in time cannot rely on the input that comes later. Okay, that's causality. Most of the physical system, actually probably every physical system, is causal. Think of the RC circuit. How am I going to know what voltage will be applied at the input in the future and react to it now? I don't know. I can't build a system like that, right? You would have to predict the future. On the other hand, the moving average filter we have here, is it causal? Does the current value only depend on the current input and the previous inputs? Which one disrupts that property? Which term? Which of the three terms? That's the future term, right? So that means this is not a causal system. What's the problem with a system that's not causal? Well, if you're doing this in real time, so if you are trying to filter out an incoming signal, okay, as it arrives, then you couldn't implement this because I don't know what's going to arrive at the next time instant, right? So if I then want to build some variant of this filter, I would have to start with perhaps x of n, add x of n minus 1, and x of n minus 2. That way you don't look at the future, okay? On the other hand, if you're doing this offline, you have data collected already, okay? And you look at your data and you see a lot of noise on it and you want to sort of average out and clean it up, then you can do that because that means just look at the next value of the data in your array, right? So it depends on the application, but in real-time applications that require physical constraints, typically you'll have to be causal. All right, is causality clear? Makes sense? Okay. So next one is stability, and I think in 16 we talk about a version of this. There are many different definitions of stability. All of them boil down to similar concepts at the end of the day. But for this course, where a system is one that just takes in an input and spits out an output, the definition is very much input-output based, right? Basically, stability means bounded inputs generate bounded outputs. So if I can give you one input signal that doesn't blow up to infinity, always remains between two numbers, right? And yet the output can grow to infinity, that's an unstable system, right? So what defines stability is any bounded input will give you a bounded output. That's it. So some people call this a bounded input, bounded output stability property, but that's the definition of stability we use. So let's go back and look at the examples. Are these guys stable? Look at the moving average filter, discrete time. Don't worry about continuous time yet. If the input signal is bounded, let's say it's always between negative and positive 1, right? What can you say about the output? That too is bounded. In fact, the particular, averaging operation we're doing here says that it also remains between the same bounds. Yes? No, we're not saying that. high pass simply means that, quickly changing components in the signal were erased, were eliminated, right? That doesn't mean anything started blowing up, right? So, it's easy to argue for the moving average filter that it's a stable system. It's analytically less easy or less obvious right now that the differential equation. What is going on? Okay, so the differential equation describing the RC circuit that happens to have this stability property. We'll talk about those later. Okay, you don't have to see that right away. But your physical intuition should tell you that you shouldn't expect any unbounded output here. Where is the energy going to come from, right? So you're applying some voltage. It's going through these dissipative elements, R, and then you're looking at the voltage. Why should the voltage blow up, right? There's no apparent reason. And we'll see some analytical methods later to convince ourselves that this is indeed a stable system also. Can you give me an example of an unstable system? Unstable, maybe I should define it. Guess what the definition is? Not stable. Well, let's be precise, okay? Because the definition of stability says for every bounded input, the output is bounded, right? So what would be the negation of that? There exists at least one input somewhere, a malicious one, right? That can drive the output unbounded, okay? So there exists. That doesn't mean every bounded input you apply will take the output to infinity. That doesn't mean that at all, okay? It just says that you can find an input, a bounded input, in fact. There exists a bounded input that makes output unbounded. So in that sense, it's a lot easier to argue instability, in a sense, than stability, right? All you have to show me is one example. Show me an input that's bounded that made the output unbounded. You're done. It's unstable, right? For stability, you have a lot more convincing to do, right? So you have to convince me that no bounded input is going to drive you unbounded. Okay? That's why we need some tests, some methods to judge stability. But arguing instability is usually simpler than that. And for that reason, you should be able to give me an example. What would be an example of a system, a simple system? Yes. Okay. So an integrator, right? So let's just say dy dt is equal to x of t, right? So give me one example, and let's say we start at 0. So the output started at 0, right? Give me an input signal that you can apply that itself is benign, it's bounded, and yet the output goes unbounded. Apply 1, right, or 2, whatever you want, right? It will get integrated, it will grow linearly, right? Does that make sense? So if I apply as an input a step, you see that, right? X of t, then the output will start at 0 and it will keep integrating 1. So it will look like y of t equals t, right? And clearly that's not a bounded signal. So an integrator is unstable. I didn't have to apply a fancy test. I just found an input that shows instability. If I apply 0 as the input, then what happens? Output is 0, so there is an input that itself is bounded and keeps the output bounded, right? Or if it was a sinusoidal, still the output, if it was sine, it would be cosine, something like that, right? So there may be inputs that are themselves bounded and keep the output bounded. All I need is one example where that's not true. So what would be the discrete time counterpart of an integrator? So in discrete time, it's called an accumulator. Am I writing this correctly, spelling? This one, or you? Okay. Are you spelling B? But two C's, right? Accumulator. So basically, y of n is a sum of x. Let's use a dummy variable k, where k goes from negative infinity to the present time, right? So that's the equivalent of an integrator, but in discrete time. Okay? So similar to integrator in continuous time. So again, this is unstable because I can apply a constant but non-zero input, and at every time you add that input to the previous one, and so this keeps ramping up to infinity. Okay? Can you find a way, can you tell me a more succinct way of writing this, expressing this accumulator mathematically with an equation that doesn't involve this infinite sum? Because I freak out when I see summation and work in infinity or something. Can you write it as a difference equation? Think about how you would implement this, right? At every new time instant, you receive a new input. You have to add it on top of the previous output, right? So you're incrementing by the input at every time. So what would be a difference equation that describes this operation? Yes? Why one for what is one for? Huh? X of n. Okay, say it again. Let me have you finish. One plus y. Why? Where is that? What is that one there? Oh, x. Oh, if the input is there. I see. Okay. All right. Okay. Yeah. Okay, I get it now. Y of n minus 1 plus x of n, right? Yeah, so that's a difference equation. It's more customary to put all variables with the same label, y in this case, on the same side, so we will just write this as in this form, right? So the solution of that is, of course, this. So they are alternative representations of an accumulator, okay? All right, so we talked about memory, we talked about causality, we talked about stability, and the next property is time invariance. And that's, the definition is fairly easy. So basically a shift, or I'll write it this way. Okay, so I apply the signal x of t, and the output came out to be y of t. If I take the same signal, drag it or shift it, apply it a little later, right? Capital T seconds later, how does the output change? If it changes in a way that's consistent with how I change the input, so y also got delayed by the same amount, then we call the system time invariant. Okay? Or TI. The opposite of that would be time varying, which would be TV. So basically what this means is that the system is consistent in what it does and doesn't change its behavior over time. Okay? If I apply the same input that I applied today, instead tomorrow, I get the same output that I got today, but tomorrow. Okay? If the behavior is changing over time, then you lose this time invariance property. Right? Does that make sense? Can you give me an example of a time invariant system? Can be silly. It's silly. Don't try to be sophisticated. Time invariant. Say that again. So y of t equals. Okay, tell me time varying. Okay. Wow. Okay. What about Let me go to discrete time actually. So, to be consistent. So x of n, so y of n equals x of n plus x of n minus 1, right? Or even the moving average example, right? The operation, the rule that I apply to generate the output doesn't change with time, right? It's always the same rule. Look at the input now, look at the previous input, add them up, that's your output. Same thing with the moving average example, right? So if I apply the same signal tomorrow, I'll get the same output. Only tomorrow. So that's basically what that suggests, right? So what would be a system that is time varying then? You have a good one. Y of n equals, say, something like n times x of n. Okay? The rule is take your input, multiply it with the current reading on your clock, on your watch, right? And obviously that rule changes with time. As n changes, you'll do something different. Make sense? Okay? So what about going back to our transformations we were talking about of the variable? So what if I defined a system to do the following? Suppose a system is defined by this operation, defined by y of t is x of 2t. Let's first see, actually I meant to talk about this operation and how it changes the signal. If you take the time variable and multiply it by a constant, what does the signal look like then? Let's do that first. So let's get a pictorial understanding of this operation, right? So let's go back to our example x of t, which looked like this, if I'm being consistent, right? So it was something like that, right? X of t. What does x of 2t look like? Let's say this is negative 2, and this is, what a horrible drawing, sorry. Okay, now I'll try to be tidier. 1, 2, 4. Okay, that's better. Okay, x of t is this. Somehow it started at time negative 2 and ended at 4, right? What does x of 2t look like? You compress it, right? So it's going to now start at negative 1 and end at 2. So this I should have added to the operations, the transformation of the time variable we were discussing earlier, like the drag and flip, all that stuff. So we would call this, by the same token, we would call this the compress operation. And what would it look like if I now looked at x of t over 2? Then you stretch it by 2, right? So 2, 4, and let it go all the way here, right? So that would be a stretch. But anyway, so the system is defined as one that compresses in time. Is this a time invariant system or a time varying system? Here is how you argue about time invariance. Again, if I apply a signal now, x of t, and it gives me some output y of t, applying the same thing a little later will generate the same output shifted by the same amount, right? So think about this when you're trying to reason about whether or not this is a time varying system or time invariant system. let's say, so this basically x of 2t is our output now, right? This is our y of t. So this x gave rise to this y, right? Now let me take that x and shift it a little in time. Some random amount, I don't care how much. Let's say, 2 units. Okay, so this is x of t minus 2, right? Negative 2 is now happening at 0, and this is 6, right? Now what happens if I apply the compress operation? What is the output if this signal, if this waveform is the input? You know what the system does, right? Looks at whatever is there, compresses it by a factor of 2 in time, right? So what should it look like? Peak happens at 1, ends at 3. We compress it, right? Okay, so that's the output to an input of this form. Does this output look like this output shifted by 2 units? If it does, I made a terrible, oh gosh, I picked the worst possible shift in time. Goodness. Oh my gosh, okay, I have to fix this now. So let's say, that was really stupid. It does look like that, right? Or does it not? Why? It's shifted by 1, that's right, yeah, okay, you're right, okay. Alright, so this looks like the same thing shifted by 1, not 2, right? So basically this type of operation really depends on when you're doing the operation, right? So therefore this is a time varying system. So the key here is that this is not y of t minus 2, okay? And therefore, again, finding one example is enough. It shows that, the system is acting differently tomorrow than it's acting today. So this is a time varying system. All right, any questions? Is the stock market time invariant? Do I get the same? If I buy G stocks now, do I get the same yield that I would get 10 years ago? That's probably one of the worst time varying systems, right? If you're on the losing end, of course. And that's basically a system where you try to take advantage of the time variations to make money. All right, so last and one of the most important system properties is linearity. For us to call a system linear, it has to satisfy two properties. Must hold. One, if you apply any input and get, if you apply an input x of t and get y of t, then scaling the same input by a number a times x of t, should give you an output that's scaled by the same amount. Okay, so if I scale the input by a certain number, scale the amplitude, multiplied by 10, the output is also multiplied by 10. Okay, so this is called the scaling property. And the second thing that needs to hold is if we have now two test signals, x1 of t gave rise to y1 of t, and x2 of t gave rise to y2 of t, then their sum, x1 plus x2 of t, adding the two signals and applying it as an input, should give you an output that's the sum of the two individual outputs. Okay? And that property is called the superposition property. Right? So let's take a static system as an example. Static meaning memoryless system. Okay. So let's say y of t is 10x of t plus 1. Okay, so basically this is describing a relation of this form. It's, when x is equal to 0, it's 1, and then it has this slope. Is this a linear system? Well, if I apply as my input, let's check the first property even, right? If I apply, say, 0 as my input, if I apply this, what do I get? Y is 1, right? If I multiply the input by 10, x is still 0, but what is out? Well, wait, that's not an example. So, yeah, 0 is not a good example actually. So let's look at a different number. So let's look at x equals 1. If I apply x equals 1, what I get is 11, right? If I scale the input by 10, what do I get? 101, right? So obviously the output didn't scale by the same factor. It was close, but not, because what really destroyed the linearity property was this bias term here, right? If it really passed through 0, this would have been linear. So technically this is nonlinear, although it kind of, if you twist your eyes, if you ignore what it passes through at 0, it kind of looks linear, but it's not. Whereas if I look at this relationship, which passes through 0, it would have been linear. So, what other examples can we talk about? If I give you y of t equals x of t squared, is that a linear relationship? You're squaring it. Clearly, things don't scale linearly, right? The scaling property will already fail. Any other examples in either direction, linear, nonlinear? Do you want to contribute something? Say that again? No, because we can talk about linearity of systems with memory. We can think about linearity of all kinds of different systems. It's not, we're not necessarily talking about, memoryless functions, right? But for a function, yes, absolutely. We will do that. But let's first make an observation. So as a result of this scaling property, right? If I choose A, right? So what we need to have for linearity is that no matter what A I choose, I have this property, right? So what if I choose A to be 0 in particular? Then the input becomes 0, right? So this reads 0 input gives me 0 output, right? So that's basically a necessary condition for linearity. If you're applying a 0 input and getting something different, which is exactly what was happening here, there was a bias term, then it's already not linear. This is a very quick and simple way of determining that something is not linear, right? So it's a corollary of the properties of linearity. So corollary of linearity is if the input is 0, the output must be 0. And how do I prove this corollary? Choose A, 0 in the scaling property. Okay, you didn't see that. So this corollary would have been enough to look at this example of 10x plus 1 and say, no, that's not linear, without even doing this silly calculations that I did. Okay? So let's talk about other examples. So let us talk about the moving average filter. Is it linear? So y of n was an average of x of n minus 1, x of n, and x of n plus 1, right? Is that linear? So if I apply an input signal like this, then comes an output signal. And then if I scale the input, so this is x, right? This is y. If I scale the input by a certain number, will the output be scaled by the same number? That's the first property that needs to hold. Anyone? Yes? Why? Because of the rule, right? So you average over x. So if I take the same x multiplied by 2, everything on the right hand side gets multiplied by 2. Therefore, y is twice as much as what it was before. So the scaling property is there, right? What about the additivity? Well, for additivity, you look at two signals. x1 gave us y1, right? So y1 of n, I applied a certain input, x1 as a function of n, and what the output that it gave me was x1 of n minus 1 plus x1 of n plus x1 of n plus 1, right? And then I applied another input, x2, and it generates this output. x2 of n minus 1 plus x2 of n plus x2 of n plus 1. Now, if I apply a new input that is the sum of these two inputs, x1 and x2, the output will be, again, there's one rule to generate the output, average over 3 values, right? The output will be 1 over 3 x of n minus 1, which is the same as x1 of n minus 1 plus x2 of n minus 1, right? Plus x of n, and that is x1 of n plus x2 of n, and plus x of n plus 1, and that's x1 of n plus 1 plus x2 of n plus 1, right? Okay? Do you agree that this is the same as y1 of n plus y2 of n? If I take this and this, add them up, indeed what I get is going to match this expression. So the scaling property is also there. So this moving average filter is certainly a linear system. Okay? It's also a time varying system. So I told you that the purpose of the moving average operation is to kind of filter out the outliers, right? So if you have ripples, if you have noise on your incoming signal, by averaging, you smooth the signal, right? So it's a low pass filter or an averaging filter in that case. So there's another way to do this. It's called the median filter. Do you know what a median means? Yes? No? Really? Nobody heard of it? Come on, you take exams and they tell you the average, the median. You never wondered what median was? If you order from lowest to highest, the one that is in the middle is the median. If you have an even number of data and there are two things in the middle, you take their average, right? But if it's odd, it's easy to define the one in the middle. So let's define a median filter again of, x of n, x of n minus 1, and x of n plus 1. This does something similar, right? I mean, the first one, the previous example was averaging. This is taking the median, just like your exam scores, right? The medians and, the averages are not too far apart from each other. They are usually a little different, but let's use this notation med for median. Okay? So, first question, when would you use a median filter like this rather than the averaging filter? Yeah, when you have huge outliers, like, you all get like, I give you an exam, this won't happen, but I give you an exam where, most of you get something between 0 and 20 out of 100. It won't happen, I promise. And then somebody gets 100, right? That's a huge outlier, right? So, so when I look at three numbers and take the median, if the data was like all zeros and then 100, right? What would the median be? So let's say the impulse is our input. X of n is delta. And let's give it a ridiculous value, 100. Okay? And everybody else got 0, right? So when I apply this median, what do I get at the output? Again, this means I have a window of length 3. As I slide through the data, I'm taking the median of 3 consecutive numbers, right? What do I get at the output? So at time equal to, say, -1, I'm taking the median of 3 numbers. This guy, and this guy, right? What is it? 0, 0, 100. What's the median of those? 0, right? So time -1, I get an output that's 0. At time equal to 0, I'm taking the average of 0. I'm taking the median, sorry, of 0, 100, and 0. What is it? Again 0, right? So you'll get all these zeros, right? 100 will be completely discarded because it was such an outlier. If I was doing the moving average filter, what would I get? I would get zeros for a while, and then at time equal to -1, what would I get? Now I'm averaging these guys, right? So this, and that. What's the average of these? 33 point something, right? Time equal to 0, I again get 33 point something, and then 33, and then it eventually is forgotten, that outlier. But the outlier did affect us in a significant way, whereas the median filter completely eliminated it. So if you're expecting huge outliers in your data and you don't want them to contaminate your data, median filter is a good way of doing it. Otherwise, the standard linear averaging filter is fine. The question is, though, is this linear? Okay, your intuition says no, but if this was an exam, you would have to convince me that your answer is no, and that would mean, how would you convince me that it's not linear? One of the two properties, scaling or superposition, has to fail, and you have to give me an example where it fails. You'll have a hard time failing the scaling property, because if I scale the input, then the output gets scaled by the same amount, right? So it is there, so I don't see a problem with that. But you can create an example where you apply 2 inputs. Look at their outputs. Then you apply the sum of the 2 inputs, and the output that you get is not going to match the sum of the 2 outputs. Okay? I will not belabor an example here, but I promise in your notes there will be one, and take a look at it and make sure you understand. So it turns out this is not a linear system. This is non-linear. Okay? Is it time varying or time invariant? Time invariant. Again, the good question, the good test for this is to ask yourself, what is the rule that I apply to generate an output from the input? And does that rule change as the time progresses, right? It's the same rule. You just take the median of the past value, the next value, and the present value. It's the same rule when I reach the end of this data or if I'm at the beginning. So this is nonlinear but time invariant. Time invariant. All right. So we talked about memoryless systems or systems with memory, causal systems. What else did I talk about? Stable systems. And the last two I talked about were time invariant and linear. When those two properties come together, it's a very powerful mix. And they create a class of systems that we call linear time invariant, LTI. Definition: linear plus time invariant. The moving average filter example is linear and time invariant, so it's LTI. The median filter example is not LTI because it fails one of the two conditions. It's not linear. So why do we care about LTI systems? Are they really, the most important class of systems? They are not. There are many systems that are not LTI. But for LTI systems, we have very powerful tools. They are extremely amenable to analysis. We can make predictions about how they behave in very, very, very simple ways. And there's a whole theory about them. Okay? For that reason, and because also some nonlinear systems can be approximated with linear ones around a given operating point, so we often want to study linear systems, linear time invariant systems, and learn the complete theory for those, and that's what this course will do. So one striking property about linear time invariant systems is the following. If I know, we talked about the unit impulse signal, right, delta of n. So let's say I have an LTI system. And as a test input, I applied the unit impulse, delta of n, as my input. Okay? And something comes out of that. Okay? For example, if it was the moving average filter, we decided that the output would be 1/3. And then all zeros. Depends on what the LTI system really is, but there is an output, right? So this is called the impulse response because it's the response of the system to an impulse. Okay? And this is so important for an LTI system that you will reserve a letter of the alphabet, and then that means, right? 20 something, how many? 26. So we'll reserve one of them in this course. Not even a Greek letter, an actual letter. So h of n will be the impulse response of an LTI system. Okay? So the key, remarkable, very important property of LTI systems is that if you know the impulse response system, if you know how your LTI system responds to an impulse, you know everything you need to know about that system. Everything can be inferred from this piece of information. You can predict the output to any other input just by knowing how it responds to an impulse. Isn't that crazy? It's pretty remarkable, right? Look at the median filter, which is not linear. What is the impulse response of the median filter? We have it up there, in fact. Yes? 0, right? All zeros. So does that have any information? Can I predict the behavior of the median filter to any input? Its response based on that all zeros? No, of course not, right? So clearly this is a remarkable property, and it's possessed by linear time invariant systems. Okay? So impulse response is very important. So I have to substantiate my claim. I told you that if I know the response to an impulse, I can generate the response to anything else. How do I do that? Okay? It's actually very simple. So I know that I applied delta of n, and what came out was h of n, right, as a signal. And then I apply something else, x of n. What comes out? What is the output? What is y of n? My claim was that if you know h of n, and if you know the new input x, you can generate that output. How do I generate it? So I can write x of n in this form, right? X of n is the value of the signal at time 0 times a delta function plus the value of the signal at time equal to 1 times a delta that is centered at time 1. How would I write it with delta? Delta of n minus 1, right? And then, x of negative 1, delta of n plus 1. And of course, it keeps going in all these directions, right? So this piece alone is basically giving you this signal, x0, and everywhere else it's 0, right? This piece is giving you a signal that's x of 1 at time equal to 1, and everywhere else it's equal to 0, right? And when I add up all these pieces, I reconstruct my x of n, right? So you all agree this is a legit way of expressing x of n, right? All right, so x of n then is equal to a summation over k. I'm just going to write this sum in a more fancy way. X of k times delta of n minus k. Do you agree? All right. So now we have a linear system, right? There's the scaling property and there's the superposition principle, right? So the input itself is a weighted sum of some signals, right? Delta signals. Okay? So linearity would then tell you that you will get at the output, again, a weighted sum by the superposition and scaling properties. You'll again get a weighted sum of the individual responses to those inputs. But you know the individual responses. If I give a delta, the output is h of n minus 1. If I give a delta of n minus 1, what is the output? H of n minus 1. Okay, what property did I use in saying this? Time invariance. So that's why we need linearity plus time invariance together. So therefore, y of n that results from this is going to be, so these x of k's are basically just coefficients of signals delta, right? So you get those same scaling factors, but the response to each delta is an h, and it's h of n minus k, right? So this is how you generate the output. You do this sum, you sum over all k's, x of k times h of n minus k, all right? So that means if I know the impulse response, I know the response to anything else. I've defined without telling you something very important. This is called a convolution. Okay? And there is a notation for this operation. We use the star notation. So x convolution h of n is basically what I just defined. This is a sum from k negative infinity to k positive infinity of x of k, k being our dummy, times h of n minus k. In your first lab, which is going out today and will be